Welcome to this lecture on topological stability from a measurable viewpoint, based on the paper by Kyunhee Lee, Sunghee Lee, and Carlos Morales. We will explore how classical stability in dynamics can be generalized when one takes a measure-theoretic perspective. Introduction and motivation. Topological stability, introduced by Walters, captures robustness under small perturbations. The classical definition is purely topological, treating all points equally. However, many systems have natural invariant measures, and we often care only about the behavior of almost all points. This motivates a measurable version of stability that depends on a Borel probability measure. Classical topological stability. Walters defined a map as topologically stable when any nearby system can be continuously conjugated to it by a small correction map. For example, expansive homeomorphisms with the shadowing property, such as Anosov and Morse-Smale systems, satisfy this condition. This theory forms a bridge between structural stability and pure topology. Measure-theoretic setting. In a measurable framework, we replace the space of points by the space of Borel probability measures. This allows us to discuss stability, on average, or almost everywhere. The idea first appeared in measurable versions of shadowing and expansivity developed by Lee and Morales. Earlier, measure-theoretic approach. A previous approach used set-valued maps that were upper semi-continuous and compact-valued. The measure of the domain was required to be almost full, and the map had to conjugate the perturbation back to the original one. This provided a measurable extension of Walters's theorem, but remained technically heavy. New definition of mu topological stability. The present paper replaces the set-valued framework by a more direct measurable one. A map is mu topologically stable if, for small perturbations, there exists a continuous correction map defined on a compact invariant subset of large mu measure, satisfying the conjugacy relation approximately. This definition parallels the classical one, but tolerates exceptions of small measure. Related concepts. To analyze measurable stability, the authors introduce M-expansivity and mu shadowing properties. They describe how pseudo-orbits that are almost valid can be approximated by true orbits on large measure sets. These notions generalize expansivity and shadowing from topology to measure theory, making them suitable for probabilistic stability analysis. Main theorem. The main theorem presents 7 properties. First, a point is topologically stable if and only if its Dirac measure is mu stable. Second, the stability set is invariant under absolute continuity, and for expansive maps it is convex. Third, for manifolds of dimension, at least 2, finitely supported measures lead to the mu shadowing property. Fourth, stability is preserved under topological conjugacy. Moreover, for non-atomic measures, mu stability implies the earlier set-valued stability, and expansive maps with weak M shadowing are automatically mu stable. Interpretation of the theorem. These properties show that measurable stability is robust, both dynamically and probabilistically. Convexity means that if 2 measures give stability, so does any mixture of them. The invariance under conjugacy ensures that the property depends only on the dynamics, not on the coordinate system. Thus, measurable stability behaves like a natural extension of Walters's concept. Examples and consequences. If a map is classically topologically stable, then it is mu stable for every measure. However, there exist examples where M stability holds for some measures but not in the set-valued sense, showing that the new concept is genuinely different. On the circle, both rational and irrational rotations fail to be mu stable, illustrating how minimal dynamics prevent any measurable correction. Conceptual significance. The measurable perspective allows us to speak of stability almost everywhere, connecting deterministic and statistical ideas. It reveals that even when a system is globally unstable, its dynamics may be stable on a subset of full measure. This unifies notions from topology and ergodic theory, offering a bridge between qualitative and quantitative dynamics. Connections and open questions. This theory extends Walters's theorem, connects to measurable shadowing developed by Lee and Rojas, and to pointwise stability studied by Koo, Lee, and Morales. Several open problems remain. Whether mu stability for all measures implies classical stability, how it interacts with ergodic decompositions, and whether it can be extended to flows. These questions suggest that measurable topological stability could form a foundation for a broader probabilistic theory of robustness. References. The main reference is Lee, and Morales, Topological Stability from a Measurable Viewpoint, together with related works by Walters, Morales, Lee, and collaborators on expansive measures and shadowing theory.